Tonight, let your mind wander outward, past the familiar glow of Earth and Jupiter, past the rings of Saturn, until the sun is a pale, distant lamp. Two strange, quiet worlds wait there, pale blue, cold, and oddly stubborn. They are Uranus and Neptune, the ice giants. Not gas giants like Jupiter and Saturn. They're composed of a thicker mix of water, ammonia, and methane, slush and ices under pressure and cold, with a thin skin of hydrogen and helium above. These planets hold fossils of the early solar system and puzzles that still tangle scientists' minds. Imagine them as faraway rooms in a house you only just discovered. Each room is dimly lit, filled with slow currents, odd instruments, and curious unanswered notes. Tonight, we listen. Uranus is the sideways planet. Its rotation axis tilts by roughly 98 degrees, so it rolls around the sun like a tipped toy. This extreme tilt means seasons that last decades. One pole basks in continuous sunlight for half a Uranian year, while the other sleeps in long winter. Then they switch. The tilt itself is one of Uranus's key mysteries. Classical explanations favored a giant ancient impact that knocked the planet over, but newer models suggest gentler scenarios. Perhaps the loss or migration of one or more large moons nudged Uranus into its tilt without a single catastrophic collision. Both ideas are active areas of research. Under that odd tilt, the atmosphere whispers storms and strong winds. Voyager 2's flyby recorded winds reaching hundreds of miles per hour, powerful but usually far slower than Neptune's. Uranus appears unusually cold, and for decades after Voyager, seemed to radiate little internal heat compared with its sibling planets, which puzzled scientists, because planets generally retain heat from formation. Some recent observations and models hint that Uranus might hide modest internal heat under seasonal layering or long timescale circulation, but the question remains open. Did an ancient event stifle Uranus's internal convection, or do we simply lack the observations to see the deeper warmth? Uranus's magnetic field is another oddity. It isn't aligned with the rotation axis and is significantly offset from the planet's center. The field seems to come from a shell of conducting fluid, perhaps a salty, ionic ocean of water, ammonia, and other volatiles, rather than from a deep core like Earth's. That geometry produces magnetic footprints and magnetospheric behavior unlike those of the more familiar planets, and it makes Uranus a laboratory for magnetism born from unusual interior flows. Uranus also hosts a set of thin, dark rings and many small moons whose surfaces record impact histories and internal variability. Some moons show signs of past heating and resurfacing. Miranda, with its jumbled cliffs and terraces, looks like a witness to violent rearrangement. These satellites may hold clues to Uranus's past, whether it was struck, spun, or had a moon wander away. Neptune sits a bit farther out, yet it behaves differently. Voyager 2 found Neptune to emit more energy than it receives from the sun, an internal heat source that feeds powerful atmospheric motions. Those motions produce the fastest winds in the solar system, jet streams and storms that push cloud features at over 1,000 miles per hour, sometimes even supersonic relative to local sound speeds. We still debate why Neptune retains or generates more internal heat than Uranus. Perhaps differences in formation, interior structure, or a quieter early collision history left Neptune's core and mantle to convect more freely. Neptune's magnetic field is another oddity. It isn't aligned with the rotation axis and is significantly offset from the planet's center. The field seems to come from a shell of conducting fluid, perhaps a salty, ionic ocean of water, ammonia, and other volatiles, rather than from a deep core like Earth's. That geometry produces magnetic footprints and magnetospheric behavior unlike those of the more familiar planets, and it makes Uranus a laboratory for magnetism born from unusual interior flows. Uranus also hosts a set of thin, dark rings and many small moons whose surfaces record impact histories and internal variability. Some moons show signs of past heating and resurfacing. Miranda, with its jumbled cliffs and terraces, looks like a witness to violent rearrangement. These satellites may hold clues to Uranus's past, whether it was struck, spun, or had a moon wander away. Neptune sits a bit farther out, yet it behaves differently. Voyager 2 found Neptune to emit more energy than it receives from the Sun, an internal heat source that feeds powerful atmospheric motions. Those motions produce the fastest winds in the solar system, jet streams and storms that push cloud features at over 1,000 miles per hour, sometimes even supersonic relative to local sound speeds. We still debate why Neptune retains or generates more internal heat than Uranus. Perhaps differences in formation, interior structure, or a quieter early collision history left Neptune's core and mantle to convect more freely. Neptune's magnetic field is another oddity. It isn't aligned with the rotation axis and is significantly offset from the planet's center. The field seems to come from a shell of conducting fluid, perhaps a salty, ionic ocean of water, ammonia, and other volatiles, rather than from a deep core like Earth's. That geometry produces magnetic footprints and magnetospheric behavior unlike those of the more familiar planets, and it makes Uranus a laboratory for magnetism born from unusual interior flows. Uranus also hosts a set of thin, dark rings and many small moons whose surfaces record impact histories and internal variability. Some moons show signs of past heating and resurfacing. Miranda, with its jumbled cliffs and terraces, looks like a witness to violent rearrangement. These satellites may hold clues to Uranus's past, whether it was struck, spun, or had a moon wander away. Neptune sits a bit farther out, yet it behaves differently. Voyager 2 found Neptune to emit more energy than it receives from the Sun, an internal heat source that feeds powerful atmospheric motions. Those motions produce the fastest winds in the solar system, jet streams and storms that push cloud features at over 1,000 miles per hour, sometimes even supersonic relative to local sound speeds. We still debate why Neptune retains or generates more internal heat than Uranus. Perhaps differences in formation, interior structure, or a quieter early collision history left Neptune's core and mantle to convect more freely. Neptune's atmosphere is a composer of dark spots and bright clouds. Voyager 2 imaged dark vortices, storms like great transient hurricanes, and smaller bright methane clouds that form and vanish. Modern telescopes and instruments have revealed that Neptune's atmosphere isn't static. Its temperatures and stratospheric conditions have shown surprising changes across decades, including warming episodes of the poles in recent years. These temporal shifts remind us that even distant worlds can be dynamic on human timescales. Like Uranus, Neptune's magnetic field is strongly tilted and offset, pointing to dynamo action in a shell rather than in a central core. That structure, a magnetic field born in a convecting, conducting layer at moderate depth, offers a unifying hint. Both ice giants may generate magnetic fields by similar processes, even while their thermal and rotational histories diverge. The contrasts between Neptune's active interior and Uranus's more subdued thermal signature are central to current theories of planet formation and evolution because they show how small differences early on can produce very different planetary lives. If we could descend beneath the pale clouds of Uranus and Neptune, the journey would not be smooth. There is no solid surface waiting below. Instead, pressure rises gently at first, then relentlessly, compressing gases into fluids and fluids into exotic states of matter that behave nothing like water or ice on Earth. Both Uranus and Neptune are called ice giants, not because they are frozen solid, but because much of their mass is made of substances that were ices in the early solar system: water, ammonia, and methane. Deep inside, these materials are crushed into dense, hot mixtures, thick, dark oceans without waves, layered by pressure rather than temperature. As we sink deeper, water itself may transform. Under extreme pressures, simulations and laboratory experiments suggest the formation of superionic water, a strange state where oxygen atoms lock into a crystal lattice while hydrogen ions flow freely, almost like a liquid electric current. This state could conduct electricity efficiently and may play a role in generating the planet's unusual magnetic fields. Unlike Jupiter and Saturn, whose mass is dominated by hydrogen and helium, Uranus and Neptune likely have relatively small rocky cores surrounded by vast mantles of this hot, icy fluid. But even this picture is uncertain. Scientists still debate how sharply these layers are separated, or whether the interiors are more smoothly mixed, a slow gradient of composition rather than clear boundaries. These unknowns matter deeply. The way material moves inside a planet controls how heat escapes, how magnetic fields form, and how the planet evolves over billions of years. In this quiet darkness beneath the clouds, the biggest mysteries remain. Most people imagine a planet's magnetic field as something neat and orderly, like Earth's, aligned with its rotation and centered deep within its core. Uranus and Neptune refuse the simplicity. Both planets possess magnetic fields that are tilted dramatically relative to their rotation axes and shifted far from their centers. On Uranus, the magnetic axis is tilted by nearly 60 degrees. On Neptune, it is similarly misaligned. This creates magnetospheres that wobble and twist as the planets rotate, sweeping charged particles through space in complex, changing patterns. The cause appears to lie in the depth and location of their dynamos. Instead of forming in a deep metallic core like Earth's, the magnetic fields of the ice giants are likely generated in a shell of electrically conducting fluid, perhaps a layer rich in ionic water and ammonia, sitting closer to the surface. This geometry produces magnetic fields that are lopsided and unstable in shape. For an observer traveling with a spacecraft, the magnetic environment would feel restless, constantly rearranging itself. These strange fields interact with the solar wind in unexpected ways, shaping auroras that are faint, irregular, and difficult to predict. On Uranus, the extreme axial tilt further complicates matters. As the planet rolls around the Sun, the magnetosphere is sometimes pointed almost directly towards it, and sometimes sideways, creating seasons not just of light, but of magnetism. Understanding these magnetic fields helps scientists test theories about planetary dynamos far beyond our solar system. Many exoplanets discovered so far fall into the size range of Uranus and Neptune. In a sense, these two distant worlds are guides, quiet teachers for understanding planets scattered across the galaxy. References: NASA Voyager mission reports, Geophysical research letters, Science.
From a distance, Uranus and Neptune look peaceful, smooth blue spheres drifting in silence, but their atmospheres tell a more complicated story. Neptune is the more visibly active of the two. Its atmosphere hosts enormous storms, dark vortices that appear and fade over years, not centuries. These storms are carried by winds that race around the planet faster than anywhere else in the solar system. The energy driving them comes from below, from Neptune's internal heat leaking upward through layers of gas and cloud. Uranus, by contrast, appears more subdued. For a long time it was thought to be nearly featureless, but as telescopes improved and seasons progressed, storms and cloud bands began to emerge. Uranus does have winds, jet streams, and weather, but they are quieter, more subtle, and possibly shaped by its extreme seasonal cycles. Methane plays a key role in both atmospheres. It absorbs red light, giving the planets their blue-green color. But methane also condenses into clouds and participates in complex chemistry driven by sunlight and energetic particles. Over time, these processes darken and brighten regions of the planets, creating slow, evolving patterns. One of the most puzzling contrasts remains unresolved. Why does Neptune, farther from the Sun, appear so energetic, while Uranus seems to hold its heat close, releasing it reluctantly? Some scientists suspect differences in interior layering. Others suggest ancient impacts or formation histories that permanently altered how heat moves inside each planet. These questions do not have firm answers yet, and perhaps that is part of their power. The atmospheres of Uranus and Neptune remind us that even with modern instruments, some truths unfold only slowly, over decades of observation and patient listening.
Long before Uranus rolled onto its side, before Neptune learned to breathe out heat, the solar system was a disk of dust and gas circling a young sun. In this cold, spinning cloud, planets were not born where we see them today. One leading idea suggests that Uranus and Neptune formed closer to the Sun, perhaps near the region where Jupiter and Saturn grew. In this denser part of the disk, material was plentiful, allowing their cores to assemble more efficiently. Later, gravitational interactions, especially with Jupiter and Saturn, may have pushed them outward, scattering them into the distant orbits they now occupy. This concept is part of what scientists call planetary migration. In these models, planets do not stay put. They drift, exchange energy, and reshape the architecture of the solar system. Uranus and Neptune may be survivors of a chaotic youth, pushed outward while countless smaller bodies were flung into the Kuiper Belt or ejected into interstellar space. Another idea proposes slower formation far from the Sun, requiring long-lived disks of material. But this scenario struggles to explain how such large planets could grow before the solar nebula dispersed. The truth may lie between these extremes, involving both migration and gradual accumulation. These formation stories matter because they help explain the planet's present differences. A violent early history could disrupt internal layering, alter heat flow, and tilt rotation axes. Neptune's energetic interior and Uranus's strange stillness may be echoes of events that happened billions of years ago, frozen into their structures like memories embedded deep within their cores. Around Uranus and Neptune orbit worlds that rarely receive attention. Small moons, thin rings, and distant companions that quietly record the history of their planets. Uranus possesses a system of narrow, dark rings and dozens of moons. Many of these moons are icy, fractured, and oddly shaped. Miranda stands out. Its surface looks stitched together from broken pieces with towering cliffs and mismatched terrains. Some scientists think Miranda was once torn apart and reassembled, perhaps due to orbital resonances or internal heating episodes early in Uranus's history. Other Uranian moons show signs of subtle resurfacing and internal complexity, hinting that tidal interactions may have once warmed them. These moons are like geological journals, incomplete, damaged, but still readable. Neptune's system tells a different story. Its most famous moon, Triton, orbits backward, a clear sign that it did not form with Neptune, but was captured later. Triton is geologically active, venting nitrogen geysers and reshaping its surface even today. Its capture likely disrupted Neptune's original moon system, ejecting or destroying earlier satellites. Neptune's rings are faint and clumpy, shaped by small moonlets that shepherd ring material into arcs rather than uniform bands. These fragile structures suggest a dynamic system, constantly adjusting, never fully settled. Together, the moons and rings of Uranus and Neptune whisper clues about past collisions, migrations, and gravitational dances, quiet evidence that the outer solar system was once far more violent than it appears now. In the late 20th century, a single spacecraft transformed our understanding of the ice giants. Voyager 2 remains the only probe to have visited Uranus and Neptune up close. At Uranus, Voyager arrived during a time of extreme seasonal alignment. One pole faced the sun directly, washing the planet in uniform light and hiding much of its atmospheric structure. What appeared calm and uneventful may have been a seasonal illusion. The spacecraft revealed rings, moons, magnetic oddities, but left many atmospheric questions unanswered. At Neptune, Voyager encountered a world alive with motion. Dark storms, bright clouds, strong winds, all captured in brief moments during a single flyby. Voyager measured Neptune's heat output, magnetic field, and moon systems, but only from one angle at one moment in time. Voyager did not orbit, it did not descend. It listened briefly, then moved on. Because of this, much of what we think we know about Uranus and Neptune is based on snapshots, not long-term observation. Scientists often compare this to judging Earth's climate from a single day's weather. This limitation has renewed calls for dedicated missions, orbiters, atmospheric probes, long-duration observers. Until such missions fly, these planets remain partially hidden, like stories interrupted mid-sentence. And perhaps that incompleteness is fitting. Uranus and Neptune are not worlds that reveal themselves quickly. They require patience, silence, time. The atmospheres of Neptune and Uranus are not merely gases. They are living fluids, moving and interacting across immense scales. On Neptune, the supersonic winds that race around the planet are powered by heat escaping from its deep interior. This heat rises through layers of hydrogen, helium, and methane, creating convection currents that organize into jet streams and transient vortices. The Great Dark Spot of Neptune, first seen by Voyager, was a storm larger than Earth. It appeared suddenly, wandered with the winds, and vanished years later. Scientists believe such storms arise from instabilities in the atmosphere, where differences in temperature, composition, and rotation combine to create vortex motion. They are fluid dynamical phenomena, guided by planetary rotation, Coriolis forces, energy flux from below, and the strange layering of the ice giant atmosphere. Uranus, in contrast, seems quiet, but this is a subtle quiet. Seasonal extremes and minimal heat loss mean the atmosphere moves sluggishly compared to Neptune. Observations from the Hubble Space Telescope and ground-based infrared telescopes have revealed transient clouds, jet streams, and small storms, reminding us that even still planets are quietly alive, obeying the same fundamental physics. The methane in both atmospheres is not merely decoration. It absorbs sunlight, moderates temperature gradients, and participates in photochemistry, forming high-altitude hazes and colored clouds. When sunlight splits methane molecules, reactive fragments recombine into complex hydrocarbons, a slow, persistent chemical dance that paints subtle patterns across the planets. Even in their distance, far from the sun's warmth, these atmospheres are laboratories of fluid physics, turbulence, and energy transfer. Endlessly fascinating, endlessly patient.
One of the most profound puzzles of the ice giants is their thermal behavior. Neptune emits almost twice as much energy as it receives from the sun, while Uranus emits barely more than it absorbs. Why such a difference? Inside Neptune, heat escapes steadily from the core, rising through convective layers. The precise mechanism may involve phase transitions of ices, layered convection, or even subtle differentiation between hydrogen, water, and ammonia. Laboratory simulations suggest that heat can be trapped or released differently depending on the mixing of materials under extreme pressure. A small variation early in formation could produce the vast differences we observe today. Uranus may have experienced a catastrophic event billions of years ago that disrupted convection. Perhaps an impact caused the core to stratify, forming a thermal lid that slows the upward transport of heat. This would explain why Uranus appears so inert compared to Neptune, despite their similar sizes and compositions. Understanding these energy flows is more than academic. They govern atmospheric dynamics, magnetic field generation, and even the long-term evolution of the planet. The heat of Neptune powers its storms, while Uranus's restraint produces the calm, deep blue sphere we see. Even in the silence of the outer solar system, energy moves, quietly, invisibly, shaping worlds that are otherwise frozen in space. References: Journal of Geophysical Research Planets, Nature Astronomy, NASA Ice Giant Studies. Beneath the cloud tops lies a hidden world of extreme pressure and temperature. Hydrogen and helium form a gaseous envelope, but below this, water, ammonia, and methane mix into dense, hot ices. Not solid like frozen lakes on Earth, but slushy, electrically conductive, and strange. At pressures millions of times greater than Earth's atmosphere, water may become superionic, where oxygen atoms form a crystal lattice and hydrogen ions move freely. This exotic behavior allows currents to flow, generating magnetic fields in ways entirely different from Earth. Ammonia and methane, compressed under these conditions, also contribute to conduction and convective motions, forming a layered dynamic interior. The cores themselves remain partially mysterious. They may consist of rock and metal, but even here, the density, composition, and exact size are uncertain. Models suggest Uranus's core could be relatively small, shrouded by a thick, stratified mantle that traps heat. Neptune's core might be slightly larger or hotter, allowing energy to escape more freely. These differences, subtle but profound, explain why two planets of similar size can behave so differently over billions of years. Gravity measurements, spectroscopy, and simulations all point toward gradual, layered interiors, but nothing can fully replace a probe plunging into the depths.
Until that day, the ice giants remain distant, untouchable laboratories, whispering secrets of physics we can barely reproduce on Earth.
Around Uranus and Neptune exists something you cannot see: vast magnetic bubbles stretching millions of kilometers into space. These magnetospheres are sculpted by the planet's strange magnetic fields and by the solar wind drifting outward from the sun. On Earth, the magnetosphere is relatively stable. On Uranus and Neptune, it is anything but. Because the magnetic axes are strongly tilted and offset, the magnetospheres tumble and flex as the planets rotate. Charged particles, electrons and ions, spiral along magnetic field lines, accelerating, colliding, and redistributing energy in constantly changing patterns. The result is a plasma environment that never quite settles. Uranus is the most extreme case. Its rotation axis lies nearly sideways, meaning that during certain seasons, the magnetosphere is oriented almost directly toward the sun. At other times, it sweeps sideways through space. This creates magnetospheric seasons, cycles of compression, expansion, and reconnection, unlike anything seen elsewhere in the solar system. Neptune's magnetosphere, while less seasonally extreme, is still chaotic. Plasma flows interact with its moons, especially Triton, exchanging particles and energy. This interaction subtly reshapes both the moon's surface and the planet's magnetic environment. These magnetospheres are not passive shields, they are dynamic systems, converting rotational energy and solar wind pressure into radiation, heat, and auroral light, quiet but persistent cosmic machinery. Auroras are the visible whispers of magnetic fields, light produced when charged particles collide with atmospheric gases. On Earth, they are bright and familiar. On Uranus and Neptune, they are elusive, faint, and difficult to observe. Uranus's auroras are irregular, shifting, and often displaced far from the poles. This is a direct consequence of its misaligned magnetic field. Instead of forming neat rings, auroral emissions flicker unpredictably, responding to solar wind conditions and internal magnetic dynamics. Neptune's auroras are even subtler. They glow softly in ultraviolet wavelengths, detected only by sensitive instruments. Their faintness suggests differences in particle populations, magnetic topology, and atmospheric composition. Auroras are not merely beautiful, they are diagnostic tools. They reveal how energy moves from space into a planet's atmosphere, how magnetic reconnection occurs, and how plasma circulates through magnetospheres. Each faint auroral pulse is a data point, quietly informing scientists about invisible processes occurring far above the clouds. In the stillness of the outer solar system, these lights rise and fade, unnoticed by any eyes, yet governed by the same physics that lights Earth's skies. Over billions of years, Uranus and Neptune have been cooling, slowly releasing the heat they inherited from formation. But the rate at which they cool depends on internal structure, composition, and early events. Neptune appears to have aged gracefully, maintaining internal heat and atmospheric vigor. Uranus, by contrast, seems prematurely quiet. Cooling affects everything. As heat flow decreases, atmospheric circulation weakens, magnetic fields evolve, interior layers may become more stratified, suppressing convection further. Over immense timescales, planets can transition from dynamic to subdued, not dead, but quieter. Some models suggest that Uranus may eventually reawaken. As internal gradients shift, convection could resume more strongly, releasing stored heat in future epochs. Neptune, meanwhile, may gradually lose its energetic storms as its heat supply diminishes. These are not changes humans will witness. They unfold over spans of time so long they feel abstract, yet they remind us that even the most distant worlds are participants in a slow cosmic evolution. Uranus and Neptune are not frozen moments, they are processes. Inside Uranus and Neptune, chemistry behaves in ways that feel unfamiliar, almost alien. Pressure reshapes molecules. Temperature rewrites rules. Methane, for example, does not remain methane forever. Under immense pressure and heat, it may break apart, releasing carbon that crystallizes into diamond-like structures. Some models suggest that deep within these planets, diamond rain may fall, carbon atoms settling downward, releasing gravitational energy as they sink.
This process could contribute modestly to Neptune's internal heat, adding yet another layer to its energetic behavior. Ammonia and water also change character. At depth, they mix into ionic fluids capable of conducting electricity. These are not oceans with waves or currents you could imagine. They are slow, dense, electrically active layers, where matter flows more like syrup than water, driven by pressure gradients rather than wind. Laboratory experiments using diamond anvil cells and high-powered lasers attempt to recreate these conditions for microseconds at a time. Simulations extend these results, predicting phase boundaries and conductivity profiles. But even our best models remain approximations. The interiors of ice giants operate in regimes beyond everyday physics, where chemistry, fluid dynamics, and electromagnetism merge. These planets are not just astronomical objects, they are natural experiments, running continuously for billions of years, beyond our reach, quietly exploring physics we can barely touch.
Uranus and Neptune move through space with great regularity. Their orbits are stable, nearly circular, calm. But this calm is the result of ancient chaos. During the early solar system, gravitational interactions between the giant planets reshaped everything. Neptune, in particular, migrated outward, scattering smaller bodies and sculpting the Kuiper belt. Many distant objects still bear Neptune's gravitational signature, locked into orbital resonances, repeating patterns of motion that persist across billions of years. Pluto itself is an example, caught in a resonance with Neptune that prevents collision despite crossing orbits. This quiet mathematical harmony is not coincidence. It is the residue of a dynamic past. Uranus's tilt also interacts subtly with orbital mechanics. Over long timescales, gravitational torques from other planets cause its rotation axis to precess, slowly tracing a circle in space. This changes how sunlight falls on the planet, influencing climate cycles that span tens of millions of years. Orbital dynamics operate silently, but relentlessly. They do not forget. Once a planet is nudged, tilted, or displaced, the consequences echo forward in time, encoded in motion, preserved in gravity. In this sense, Uranus and Neptune are memory machines. Their paths through space record the story of the solar system's youth, written not in words, but in trajectories. When astronomers search for planets around other stars, they often find worlds similar in size to Uranus and Neptune. These sub-Neptunes and mini-Neptunes are among the most common types of planets in the galaxy. This makes Uranus and Neptune profoundly important. They are not exceptions, they are templates. By studying their atmospheres, interiors, and magnetic fields, scientists build models that help interpret distant worlds detected only as shadows and spectra. The way methane absorbs light, the way heat escapes, the way magnetic fields form, all of these lessons travel outward, applied to planets hundreds of light years away. Some exoplanets may be warmer versions of Neptune, with thick atmospheres and deep volatile layers. Others may have lost part of their gaseous envelopes, exposing dense cores once hidden beneath ice and gas. Understanding where Uranus and Neptune fit along this continuum helps us understand planetary diversity itself. In this way, the ice giants are no longer just distant members of our solar system. They are bridges, connecting what we can observe directly to what we can only infer. And still, they remain only partially understood. For decades after Voyager, Uranus and Neptune were mostly silent, distant blue points, changing too slowly to notice. But modern telescopes have learned how to listen more patiently. The Hubble Space Telescope has tracked Uranus through its long seasons, revealing that its atmosphere responds dramatically to sunlight over time. As Uranus moved away from solstice and toward equinox, storms appeared, cloud bands sharpened, and atmospheric circulation grew more active. This confirmed what scientists long suspected. Uranus was never truly quiet. It was seasonal. Neptune, too, has surprised observers. Long-term monitoring has shown unexpected temperature changes in its stratosphere, including periods of cooling followed by rapid warming near the South Pole. These shifts challenge existing climate models and suggest that energy transport in Neptune's atmosphere may involve slow oscillations we do not yet understand. Infrared observations have revealed subtle variations in methane distribution, hinting at deep atmospheric circulation patterns, slow upwellings and downwellings that transport material over decades. These are not storms that shout, they are movements that whisper. Each new observation adds detail, but also complexity. Instead of closing mysteries, modern data often opens new ones, reminding us that these planets evolve on timescales longer than careers, longer than missions, sometimes longer than civilizations. Some researchers believe Uranus's low heat output is the result of a single massive impact early in its history. Others argue for gradual internal layering, a compositional gradient that suppresses convection without requiring catastrophe. Both ideas are supported by models. Neither has been proven. There's similar debate about Neptune's energy. Is its heat simply leftover from formation, released efficiently? Or does ongoing differentiation, slow separation of materials by density, generate additional warmth? Some simulations support diamond precipitation as a heat source. Others suggest it is negligible. Even the structure of the interiors remains contested. Are there sharp boundaries between layers or smooth transitions? Do superionic phases dominate or exist only in narrow shells? How stable are these layers over billions of years? These disagreements persist because direct measurement is impossible, for now. Without probes descending into the atmospheres, scientists must rely on indirect clues, gravity fields, magnetic signatures, spectral lines, and numerical simulations. In the quiet halls of planetary science, uncertainty is accepted. Questions remain open not because of ignorance, but because the planets are subtle teachers. Uranus and Neptune are difficult not because they are complex, but because they are far. Light takes hours to reach them. Spacecraft take more than a decade. Missions must survive cold, darkness, and time itself. Because of this, data arrives slowly, in fragments, stretched across generations of scientists. A graduate student may begin a study of Neptune's atmosphere and retire before a follow-up mission ever launches. This distance forces humility. Models must remain flexible. Conclusions must be tentative. The ice giants teach science to slow down. They also stretch our sense of time. Weather patterns unfold over decades. Seasons last longer than human childhoods. Interior processes may change only over millions of years. These planets operate on clocks that do not match ours. And yet we continue to watch. In the faint light of distant suns, instruments gather photons, spectra accumulate, and understanding inches forward, not rushing, not finishing, just deepening. For worlds this distant, knowledge advances slowly, but scientists are already imagining how to listen more closely. Proposed missions to Uranus and Neptune often include orbiters paired with atmospheric probes. An orbiter would watch seasons unfold, map gravity fields, and trace magnetic structures over years. A probe would descend once, briefly, measuring temperature, pressure, winds, and composition as it falls, a single vertical line of truth through a vast unknown. Why does this matter? Because many of the deepest questions cannot be answered from afar. Only an in situ probe can tell us how methane varies with depth, how heat is transported upward, or how sharply interior layers are separated. Only repeated orbits can reveal whether storms are cyclical, chaotic, or quietly periodic. These missions are difficult. They require long travel times, nuclear power, patience across decades. But they promise something rare in planetary science: closure on fundamental unknowns. And yet, even these missions would not finish the story. They would add depth, not endings. Uranus and Neptune are too large, too slow, too subtle for quick answers. References: NASA Ice Giant Mission Concepts, Planetary Decadal Survey, Jet Propulsion Laboratory. When we imagine winds, we imagine motion near the surface.
But on Uranus and Neptune, circulation extends far deeper. Beneath the visible clouds, atmospheric models suggest layered convection, regions where heat rises freely, separated by layers where compositional gradients suppress motion. These compositional gradients act like invisible barriers, slowing vertical mixing. This may explain why Uranus traps heat while Neptune releases it. If Uranus has stronger stratification, heat becomes locked below, unable to rise efficiently. Neptune's interior may be more homogeneous, allowing energy to flow upward and drive storms. Waves also play a role. Gravity waves and planetary scale oscillations can transport energy sideways and upward, redistributing heat without obvious surface signatures. These waves are slow, subtle, and difficult to observe, but they may dominate long-term climate behavior. Even now, scientists debate how deep the winds go. Do jet streams penetrate thousands of kilometers, or are they shallow features riding atop deeper stillness? The answer affects everything from magnetic field generation to thermal evolution. The atmosphere, it seems, is not a single moving shell, but a stack of interacting layers, each obeying the same physics, yet behaving differently under pressure and time. In planetary science, simplicity is tempting. One wants neat categories: gas giants, ice giants, rocky worlds. Uranus and Neptune resist this. They are similar in size, mass, and composition, yet profoundly different in behavior. One glows with internal heat, the other whispers. One storms violently, the other waits. This resistance to simplicity is not a failure of classification. It is a reminder that planets are histories, not objects. Each carries the memory of its formation, its collisions, its migrations, its cooling. Small differences early on, a slightly different impact, a marginally altered composition, a brief shift in orbital dynamics can echo forward for billions of years. The present state of a planet is not just physics, it is physics plus memory. This is why Uranus and Neptune matter so deeply. They show us that even when ingredients are similar, outcomes can diverge dramatically. They caution against overconfidence. They reward patience. In their quiet distance, they ask us not to rush understanding, but to sit with uncertainty and let knowledge unfold slowly. Far into the future, long after familiar constellations have shifted and the sun has grown brighter, Uranus and Neptune will still be there, circling quietly in the cold outer dark. Over billions of years more, Neptune's internal heat will continue to fade. Its storms will slow. Winds will soften. The bright clouds that race today may one day drift lazily, guided by a weaker engine below. Uranus may change too. Heat that has remained trapped for eons could eventually find new pathways upward. Subtle shifts in interior layering may awaken deeper convection. The planet may grow more active or remain quiet, conserving its energy like a long-held breath. These changes will not be dramatic. They will not announce themselves. They will unfold so slowly that no single moment will mark them. The ice giants evolve the way deep time always does, patiently, continuously, without urgency. They do not demand attention. They do not blaze with rings like Saturn or roar with storms like Jupiter. And yet, they may be among the most instructive worlds we know. They teach us that similarity does not guarantee sameness, that early history matters, that outcomes depend on subtle beginnings. They show us that the universe is not always eager to reveal itself. Sometimes it waits for us to learn how to observe more carefully. In studying them, scientists learn humility. Models must remain open, Explanations must stay flexible. Knowledge grows not by conquering mystery, but by respecting it. These planets exist at the edge of our reach, both physically and intellectually, and perhaps that is why they feel so calming to contemplate. They ask nothing from us except patience. References: Comparative Planetary Science, Annual Review of Astrophysics. And now, as our journey begins to slow, Uranus rolls quietly in the distance. Neptune breathes out faint warmth into the dark. Their storms continue. Their interiors shift. Their magnetic fields wander. But for now, we let them be. If you enjoyed wandering through the mysteries of these distant worlds, and if slow science helps your mind settle, you're gently invited to subscribe to the Wandering Neuron. More quiet journeys through physics, space, and unanswered questions are always waiting. For now, let your thoughts drift outward, past the ice giants, and into the calm, open dark. Good night.